Hello everyone, today we'll be dealing with Module 5 Realization of FIR filter structures. Filters are of non-recursive type where the present output samples depends on the present input samples and the previous input samples. Whereas the IR filters are recursive type where the present output samples depends on the present input, past input and the output samples. Here the FIR filters allows zeros and fours, whereas the FIR allows only zeros. IR filters are not guaranteed to be stable, whereas FIR filters are always stable. A causal FIR filter is characterized by its transfer function h of z, given by h of z is equal to summation m equal to 0 to n minus 1 bm into z raised to minus n, wherein h of z is equal to y by z divided by x of z. Here, y of z is equal to summation m equal to 0 to n minus 1 bm into z raised to minus 1 into x of z. So looking at this expression, we will be drawing the direct form realization of FIR system. Here, only zero system exists in FIR filters. Let's take an example. Realize an FIR filter with impulse response h of n equal to 1 by 2 raised to n into u of n minus u of n minus 4. The impulse response of FIR system can be written as h of n equal to delta n plus 1 by 2 delta n minus 1 plus 1 by 4 delta of n minus 2 plus 1 by 8 delta of n minus 3. So here the value of n is going to range from 0 to 4 itself. So n is equal to 0, 1, 2, 3. So 1 by 2 raised to 0 is 1. Delta n coefficient is 1. So 1 by 2 raised to n, 1 is 1. So the coefficient of delta n minus 1 is 1 by 2. Similarly, the coefficient of delta n minus 2 is 1 by 4. Coefficient of delta n minus 3 is 1 by 8. Taking z transform on both the sides, we get h of z is equal to 1 plus 1 by 2 z raised to minus 1 plus 1 by 4 z raised to minus 2 plus 1 by 8 z raised to minus 3. Let h of z is equal to y by x of z. So the equation can be written as y of z is equal to x of z plus 1 by 2 z raised to minus x of z plus 1 by 4 z raised to minus 2 x of z plus 1 by 8 z raised to minus 3 x of z. Now taking inverse z transform on both the sides. So we get y of z as y of n, x of z as x of n. Z raised to minus 1 we get as x of n minus 1, z raised to minus 2 can be written as x of n minus 2, z of minus 3 is written as x of n minus 3. So let's see how we can draw the direct form one for FIR system. So this is the expression what we have got. Now look at here, we have only zero system, we don't have poles here. So x of n is an input, y of n is my output. So the coefficient of x of n is 1. So let's try to draw the structure. So here, check it out. So x of n is an input, its coefficient value is 1. But at the same time, we have to add 1 by 2 into x of n minus 1. So we need to add one delay. Check out. So it is x of n, we are getting 1 as its coefficient. We have x of n minus 1. After x of n, if you have a delay, it will give you x of n minus 1. Its coefficient is 1 by 2 and there is an addition sign. Add or summing point you can say. Next, we have 1 by 4 x of n minus 2. Again, this is x of n minus 1, n minus 2. So n minus 2 coefficient is 1 by 4. Next, again x of n minus 3. So this point is x of n minus 3, its coefficient is 1 by 8. So 3 summers, 3 delays, and together we get the output y of n. Similarly, there's one more important question which has been asked on realize the linear phase FIR filter having the following impulse response. Here h of n is equal to delta of n plus 1 by 4 delta of n minus 1 minus 1 by 8 delta of n minus 2 plus 1 by 4 delta of n minus 3 plus delta of n minus 4. Now here Whenever you get the equation in terms of delta, take the z transform on both the sides. So h of n will become h of z. So this can be written as y by x, and this is 1 plus 1 by 4. So delta of n minus 1 can be written as z is to minus 1. N minus 2 written as z is to minus 2. N minus 3 is written as z is to minus 3. N minus 4 is written as z is to minus 4. Cross multiply and you get the equation. Now, again we need to take the inverse z transform of the y of z. So we get y of n equal to x of n plus 1 by 4, x of n minus 1 minus 1 by 8, x of n minus 2 plus 1 by 4, x of n minus 3 plus x of n minus 4. Now we need to phrase an equation in this form. We need to look at the coefficients of each x of n, n minus 1, n minus 2, n minus 3, n minus 4 and combine together. So here x of n is having a coefficient 1. Even x of n minus 4 is having coefficient 1. So x of n plus x of n minus 1 plus now. So 1 by 4 is with x of n minus 1, x of n minus 3. Done. So it is only you are remaining with minus 1 by x of n minus 2. Let's see how we can draw this. So here there are 4 delays, n minus 1, n minus 2, n minus 3, n minus 4. So the z is to minus 1, minus 2, minus 3, minus 4. And x of n is your input, y of n is your output. So this is your x of n. Right. Now z is to minus 1 is for x of n minus 1, x of n minus 2, z is to minus 1, x of n minus 3, z is to minus 1, and so on. So 4 delays, I have 1 x of n. Now x of n and x of n minus 4 is having an amplitude of 1 or magnitude of 1. So here x of n plus x of n minus 4 is given to 1 added because there is an addition symbol to it. Now we need to add x of n minus 1 plus x of n minus 3. So here x of n minus 1 will be here plus x of n minus 3 will come over here. Okay, check out. So x of n minus 1 is added with x of n minus 3. So there is one more addition. Now we are only left with x of n minus 2. So x of n minus 2 will be taken from here. So x of n minus 2, which is having a magnitude of 1 minus 1 by 8. Now together we need to add and give it to added with output y of n. Check out. So x of n plus x of n minus 4. Minus 4 is having a coefficient of 1. X of n minus 1, n minus 3 is having a coefficient of 1 by 4. And x of n minus 2 is having minus 1 by 8. Together this is given to one adder, and that is the output. Let's take one more example. A linear phase FIR filter having the following response. So this is again in delta. You have to take the z transform, multiply, cross multiply, and we get capital Y of z. Again take inverse z transform of this equation and combine with the coefficient. X of n is having 1, and x of n minus 5 is 1. So add together. So look for 1 by 4 and 1 by 4. So it is minus x of n minus 1 plus x of n minus 4. If you multiply this, this will become minus. So we get minus here. But as we are taking it to bracket, it will become plus. So always there will be addition. Next, 1 by 2. So x of n minus 2 and x of n minus 3 have been combined with a coefficient of 1 by 2. So let's check its output. So as here we have 5 delays. So x of n, n minus 1, n minus 2, n minus 3, n minus 4, n minus 5. So x of n and n minus 5 should be added. X of n is added with n minus 5, which is output 1. Similarly, your x of n minus 1 and x of n minus 4. So x of n minus 1 with x of n minus 4 with the coefficient minus 1 by 4. Next, x of n minus 2 plus x of n minus 3. So n minus 2 plus n minus 3 with the coefficient 1 by 2 altogether given to one adder, that is the output y of n. Determine the direct form realization of system of the function h of z. 1 plus 2 z raised to minus 1 minus 3 z raised to minus 2 minus 4 z raised to minus 3 plus 5 z raised to minus 4. So h of z can be written as y by x, cross multiply and you get this equation. So as it is a zero system, we need to draw a cascade of this. We will not be getting poles. So check it out here. So the value of, if you take the inverse z transform of this, we get y of n equal to x of n plus 2 of x of n minus 1 minus 3 of x n minus 2 minus 4 of x of n minus 3 plus 5 of x of n minus 4. So again we have n minus 4. So 4 delays. Right. So this is what is the direct form what we have seen in the earlier session. Cascade. Again, this is one of the important part. So here we have only zero system. So we'll be drawing the cascade in terms of direct form 1 for first order as well as second order. Obtain the cascade realization of the system for the function 1 plus 2z minus 1 minus z raised to minus 2 into 1 plus z raised to minus 1 minus z of minus 2. Here, h of z is written as h1 of z into h2 of z. So your h1 of z is 1 plus 2z raised to minus 1 minus of z raised to minus 2. And h2 of z is 1 plus z minus 1 minus z raised to minus 2. So again h1 of z is y1 by x1, h2 is y2 by x2. Cross multiply and you will get this equation. Now take the inverse z transform of this equation. If you take the inverse z transform of the equation, we have two delays. Either you can go by the difference equation or you can go by the transfer function. So here x of n is my input and y of n should be my output. So I have 1, 2 and minus 1. So z raised to minus 1, minus 2. I have two delays. X of n is having a coefficient 1. X of n minus 1 is having coefficient 2. X of n minus 2 is having coefficient minus 1. Similarly, now we need to cascade this h1 of z with h2 of z. So again, the x2 of 1, x2 of z is having coefficient 1. X of n minus 1 is having coefficient 1 again. Again, x of n minus 2 is having coefficient minus 1. This is how we have to draw the cascade form. Let's take one more example. Obtain the cascade realization of the system h of z. This is the transfer function. Now you need to factorize. You get 1 plus 2 z raised to minus 1 into 1 plus 1 by 2 z raised to minus 1 plus z raised to minus 2. So this would be h1 of z. This is h2 of z. So here, as we have only one delay, so one delay with 1 and 2 coefficients add up. We need to cascade with h2 of z. We have 1 as a coefficient. X of n minus 1 is having coefficient of 1 by 2. X of n minus 2 is having coefficient of 1. So in this session, in FI system, we have done the direct form structure, linear phase system and cascade system. These are very important for your main exam. Thank you.